The question that I have is, what are the elastic methods of calculating stress changes in soil due to something like a fooding loading? Let's talk about what elastic solutions are. Supposing, say, we are interested in finding the stress changes due to a vertical point load applied at the ground level. First, we assume that the soil is a linear elastic material. Then we define the differential equations governing equilibrium. Then we define the boundary conditions and other secondary relations such as strain displacement relations. At this point, we try to solve the equations, but we find that the equations are still a little bit complicated. So what you do, you make some assumptions so that the equations can be solved analytically. The solutions obtained in this manner are what are usually called the elastic solutions. But we are lucky that this has been done long time ago. Here are the two guys that did this. Boussinesq in 1883, Westergaard in 1938. The difference between the two solutions lie in the assumptions made by them. They are slightly different from each other. Let's talk about the stress changes caused by a point load. Here is a picture from the textbook, schematically showing the details. A point load P is applied at the ground level, a vertical point load P, and this three-dimensional differential element shows the changes in the stresses. We talked about a stress having several components, right? So in principle, all of those components actually will change, but we are mostly interested in calculating the vertical settlement, and the vertical component is the one that's going to have the most influence on the value of the vertical settlement. Therefore, we'll just focus on the vertical component. Here is the solution by Boussinesq, and here is the solution by Westergaard. So here is a comparison between the two solutions. It is seen that the stress change calculated by Boussinesq solution is consistently higher than that calculated by the Westergaard solution. So the next question is, how do we take the solution for a point load and obtain a solution for a load applied over an area? Well, we use calculus. The key is integration. Well, what do I exactly mean by that? Say we have a footing of area A. Let's assume that the contact pressure Q is uniform. Then we can calculate the contact pressure by this simple equation, P over A equals Q. If I take a small differential area, the load on that area will be Q multiplied by dA. This load can be treated as a point load. We have a solution for the point load, right? So all we have to do is to integrate the solution over the area of the footing. Of course, to do this and obtain analytical solutions, the footing must have simple shapes, right? So this has been done actually for circular footings, rectangular footings, and strip foundations. First, we'll focus on these shapes. Then I'll show you how we could handle a irregularly shaped loaded area. Alright, let's discuss how to calculate the vertical stress change due to a uniformly loaded rectangular area like this one right here. It turns out that the solution is available for a point such as point A that lies directly below one of the four corners of the rectangle. Let's define two dimensionless factors, little m and little n, and write the vertical stress change by this equation, where I3 is referred to as the influence factor. Q, of course, is the contact pressure calculated by this equation. The influence factor I3 is a function of little m and little n. This chart over here presents the solution. On the horizontal axis, we have little m. On the vertical axis, we have the influence factor I3, and then each of these curves correspond to a specific value of little n. So for a given value of little m, we'll just draw a vertical line corresponding to that value and then go up to the curve that corresponds to the value of the little n, and then draw a horizontal line from that in order to get the value of I3. And of course, if you don't see a curve for the little n that you have, you're going to have to interpolate. The solution is also available in the form of equations and tables, and I would like you to refer to the book for the details on those. I want to point out one more thing before we leave this slide. This curve at the very top corresponds to a value of infinity for little n, right? So when does little n becomes infinity? When, well, L goes to infinity, right? So when L goes to infinity, what kind of footing is that? That's the strip foundation. And therefore, this curve at the very top gives you the solution for a strip footing. In other words, this chart actually contains the solution for not only a rectangular footing but also a strip footing. We'll illustrate the use of this chart through a numerical example in the next video. The way you handle a circular footing is similar. We will illustrate that through an example as well.